This video we're going to find the energy transfer by the system to the user in 24 hours and then the power transfer. So as always, let's draw our circuit. So we're going to have the resistance here and a node and a resistor and another resistor here. Well, down here we're gonna have, well, a resistance first and then a voltage source, and then here we're going to have another resistance and a diode polarized in this direction, so it's only going to allow the current flowing from down to up here, so from in this direction, so from here to here. Well, and then that's pretty much it. This one is going to be my point A, this one is going to be my point B. This is a U. This is my resistance R5. This is R1, R2, R3, and R4. So the problem is saying that for the circuit on the left, we know that V is equal to 12 volts, Ri is equal to I ohm, so 1 ohm, 2 ohm, 3 ohm, 4 ohm. Find the energy W transferred from the system to the user in 24 hours, and the power P transfer. Okay, so gonna have to find the energy transfer from the system to the user in 24 hours and the power transfer. Now, I'm gonna try to find the equivalent circuit of Thevenin at these 2 points, A and B, and the diode here is only going to allow the current flow in this direction, as I said, but notice that the current is from the voltage generator is going to flow in the opposite direction. So I can actually do 2 things before trying to find the Thevenin equivalent circuit. I'm going to redraw this circuit here, and I'm going to draw, I'm going to swap this diode with nothing. I'm just going to swap it with an open circuit, because current is not going to flow through here. It's an ideal diode. And I'm going to make it end across A and B. So my circuit is just going to be this resistance here. Then here we will still have R2 and the voltage source. Here we will still have my resistance. Down here, I'm just gonna swap this with an open circuit, because no current is gonna flow through the diode, because it's polarized in the opposite direction. As the current goes down, it stops here. So this is an open circuit. And then it stops at the point A and B. So this is still R1, this is R2, this is R3, this is R4. Well, the values, this is 12 volts, R1 is 1 ohm, 2 ohms, 3 ohms, 4 ohms. This is A and this is B. Okay, so, well, oh, and I'm gonna define this current here flowing through here as I. Now, what I said I'm going to do is that I'm going to try to find the Thevenin equivalent circuit at the point A and B. So I'm going to have to find RTH, which is the R Thevenin, and VTH, which is the voltage Thevenin, because, you know, as you may be familiar, you should be familiar with Thevenin right now, but Thevenin basically says that a circuit, no matter how complex it is, can be replaced with an equivalent circuit made by a voltage generator in series with a resistance. So let's find the value of the resistance and the voltage source. So RTH, or Thevenin, is going to be R1 in parallel with R2, all plus R3. Yeah, that's it, because no current is going to flow through R4. So R1, as I said, in parallel with R2, all plus R3, and that's it, because no current is going to flow through R4. No current whatsoever. It's an open circuit. So RTH will just be, let's plug number back into this. So 1 in parallel with 2, all plus 3. So RTH is the product over the sum. So 1 times 2 over 1 plus 2, all plus 3. So RTH is 2 times 1 is 2. Well, why did I write 3? Why did I write 3? It's the product over the sum. So 2 times 1 is 2, 2 plus 1 is 3. I was already going to write 3, but anyway, so plus 3. So now RTH is 3, 2, 3, 6, 9, so it's 9. So RTH is 9 plus 2 is 10, 11. So 11 over 3. 10, 11. So 11 over 3 is... should be 3.66, I think, but 11 over 3 is, yeah, 3.66. Ohm. Now, VTH instead will be, well, VTH will be the current flowing through R1, the voltage through R1 only. So it will be VR1. So by Ohm's first law, the voltage VIR, this is a triangle. I'm gonna find the voltage, so it's I times R. So it will be I times R. R what? I1. So VTH, well, actually I don't have I, because I do have I1, but I don't have I. So I can do, well, I can just find I by finding R total and then using Ohm's first law, which is I equal to V over R. So I can say, okay, I'm gonna find R total. So R total would be R1 plus R2, which is 1 plus 2. So R total is 3 ohm. And then I can use Ohm's first law once again to find I, which is V over R. So I is V over R total. So I is, was it 12? Yeah, 12 over R total, which is 3. So 12 over 3 is just 4 amps. Now I can actually find VTH, so VThevenin. So VTH is going to be R1 times I, as I said before, I times R1 times I is the same. So VTH is just R1, which is 1, times I, which is 4 amperes. So VTH is 4 volt. Now, we have found RTH, so the Thevenin resistance, and VTH, which is the Thevenin voltage. So we are getting there. Now we can actually draw the Thevenin equivalent circuit at a point A, B. But since I actually did it for those 2 points, A, B, in the original circuit, I'm also going to add U, which is this part here, with the resistance R5. So the Thevenin equivalent circuit, it's going to be the Thevenin equivalent voltage source in series with the Thevenin equivalent resistance. And then we're also going to have this other part of the circuit. So it's going to be like this one, but with this part, well, with like this, and then with this part here. So we're going to have, by definition, a voltage source, which I'm going to call VTH, which we had just found, and in series with RTH, which we have just found. And then we would have our point A and B, and B, and then we have to add this other part of the circuit. So basically just this resistance called R5. U. Okay, so what was the problem saying? Well, the problem was actually asking us to find the energy transfer from the system to the user in 24 hours and the power P transfer. So we're first going to find P, and then we're going to find the energy. So the power required, the power is actually, well, by Ohm's third law, power is I squared times R. Ohm's third law. So P is going to be I squared times R5. So P is actually, well, I'm just going to invert those. R5 times, how can we find I in this circuit? Well, I is just, if you cover this, I is V over R. So since it's V over R and we have two resistances here, I'm gonna have VTH, VThevenin, over RThevenin plus R5 squared, of course, is I squared. So P is R5, which was it, oh, Ri equal I, so R5 is 5 ohm. This 1 ohm, this was 2 ohms, this was 3 ohms, this was 4 ohms. Yeah, so R5 is 5 ohms. R5 is 5 ohms. And VTH is 4 volt, which we have found here, and RTH was 3.66 ohm. There we go. So P is R5, which is 5 ohm, times this volting here, so VTH, which is 4 volts, over RTH, which is 3.66 ohm, plus R5, which is 5 ohm squared. So P is 5 times, let's do all this, come on, well, we have 4 times 4, which is 16, of course, but I'm lazy, over 3.66 plus 5, which is just 8.66, of course. So P is 5 times 16 is 80 over 8.66. So P is 80 over 8.66, which is 9.23. Did I make it right? 9.23? Is it 9.23? Is it 9.23? What? Well, let me just check. Well, R5 is definitely 5 ohm. VTH was 4 volt. RTH was 3.66. And R5 is 5 ohm. We have 5 times, well, 4 times 4 is definitely 16. And, oh, well, yeah, that's my mistakes. I just added them and I forgot to square them. So it's 8.66 times 8.66, which is 74.99. I'm gonna say that it's 75. So 80. Oh no, shoot. Yeah, I still have the n's. So 80 over n's is 1.06. And now it makes sense. Okay. So now we're almost there because we have found the power. We still have to find the energy transferred from the system to the user in 24 hours. So if we are gonna use these appliances here for 24 hours, we're gonna have that the energy will be P to the power times T, which is the time constant, is 24 hours. So W is actually going to be 1.06 times 24 hours, so 24. Therefore, W is 25.44 watts per hour. So that's pretty much it for this problem as well.